Test, test. Hello, hello. Hey. How's it going? All right, I think we're going to get started. So people are still trickling in, but we're all a little bit behind. Alpha just reminded me, if you could please turn off your Bluetooth devices, I'd really appreciate it. No. There'll be no test. Thanks, Albert. Yeah, let's go to the other box. All right, okay, my name is Brett Slatkin. I'm a software engineer on the Google App Engine team. I'm going to tell you today about how to build high-throughput data pipelines on Google App Engine. And be sure, even if you don't stay for this talk, directly following my talk is another talk from Mike Isatsky, who's also on the team, that'll be talking about the new Mapper API and our kind of report generation tools. It's a really good talk you should check out also. So you can view live notes, tinyurl, App Engine pipelines, or this is my blog where you can follow me. So go on there. We also have a moderator page for questions, so you can vote on the questions you want to ask. OK, so here's the agenda for today. So I'm going to do a little intro. I'm going to talk about fan out. I'm going to talk about transactional sequences, what those are. We're going to talk about fan in. It's different. And we're going to have a little bonus round in there, because I wanted to do more. And then we'll talk about the future directions of what's coming next and where we're going next. So this is the wilderness. Every year I get to go off into the wilderness and kind of think about things and learn about new ways to count, basically, for you. I started some sharded counters and some right behind cache. And it seems like every year I kind of figure out a new way to count things. And that's because counting is actually representative of a very difficult problem. So a lot of my examples, and it's also a difficult problem that people really easily understand. So I've come back from the wilderness of about a year of experience here messing around with data pipelines because of my 20% project called PubSub, which is a protocol and system for making feeds real time. So I've had a nice chance to learn about how to build the data pipeline on App Engine where we run the Google PubSub hub. So I'm back from the wilderness. So what are pipelines? What have I learned? Well, pipelines are a constant trickle of inputs and outputs. They're an assembly line. Okay? They're optimized for the latency of that line. And usually you want it to be on the order of seconds, right? And the whole idea is to minimize the incremental cost as much as possible, right? That's how I would define a pipeline. They're also not supposed to be lossy, so it's not like halfway through the assembly line you lose a car or something like that. So it's in the same sense, you don't necessarily want to ever lose your data. You want to make sure that all inputs are served if they're supposed to be served. So what is not a pipeline? Offline systems like MapReduce, batch processing, any kind of report generation. Anytime you're doing some kind of output from a snapshot of inputs, that's not a pipeline. If you're doing year-end calculations for finance, that's not a pipeline. That's just something you do at the end of the year, right? And in that case, the latency from input to output is on the order of hours or days, not on in seconds. So to differentiate. So some actual example apps. So email delivery, Twitter, Hubbub, all kind of do routing, message routing. Those are pipeline systems. They're latency sensitive. Reddit and Dig, they do voting, and high-throughput aggregation, that's a pipeline. They want the time from when you vote to when it goes up the page to be very low. And even kind of customer relationship management software is kind of a pipeline because you want customers to move through a workflow as quickly as possible or get passed off between workflow items as quickly as possible. So there's a lot of things you can model as a pipeline that maybe aren't obvious. Things that aren't pipelines. A guest book application doesn't really do much at all, so it's very flat. Terrasort, if you're sorting a ton of data using MapReduce or some other system, that's taking a snapshot of data and operating on it. It's not a living and breathing system. And then chat is transient. You kind of throw things away, so that's not a pipeline, although it has some pipeline aspects. And then hybrid systems like basically anything where you're doing, you want you're latency sensitive, but you actually kind of have to do batch processing to achieve it. So YouTube and Vimeo both do a lot of transcoding. That takes a lot of time, but they actually can stream back frames as they're doing it. So they're latency sensitive, but also require a lot of background processing. Flickr and Picasa do this also with facial recognition. OK, so let's start off with fan out. So this is something that if you've used the task queue, you kind of have an idea of the general design pattern here. The idea of having continuations. So fan out is where you have a single action, either from a user or from some other action in your system, causing a lot of other actions to happen. So a common use of this is kind of a data store-based inbox system, where you have one person posting a record and you want a lot of other people to get it. Right? That's fan out. That's data fan out. Sometimes you also want to guarantee that notifications get there. So you want to make sure that when somebody submits an expense report or something like that, that no matter what, they're always sent an email about it, so that it never gets dropped. Also making web service calls if you're trying to communicate between systems. That's sometimes you might have one task that actually needs to do about 10 different calls and then kind of merge the results. Or in queuing more tasks to do more work. Those are kind of fan out tasks where you're branching onto multiple paths. So here's a really quick example of fan out. So let's say that I have some party that I'm putting on, and I have some party goers who are going to the party. I have here a party class. It's my data model. There's when the party is and who the host is. And then people who are going to the party. So a reference to the party, who's going, and their email address. OK, really simple. So if I have this, and then I want to send everyone an email, let me just slowly go through this. So this is a task request handler. I'm writing these in Python just because it's so much shorter, and it's easier for me to just go line by line with you. So, but all this stuff you can do in Java almost exactly the same way. Just a question of moving the white space around. So that's either a Python joke or a Java joke, depending on how you see it, right? OK, so first I find my party from the task parameters. I find a data store cursor, if there is one. I start a new query, partygoer.all filter, look for people who are going to my party. And if there's a data store cursor, I will use the cursor with that query, which basically lets me pick up where I left off on the query. Okay? And then I will send some emails. That's where that quote is, or do any kind of fan-out activity, right? And then if I've retrieved 10 partygoers, if you see query.fetch 10, I received 10 items from the query. And so if I did receive 10, then there might be more. So then I enqueue another task, which is a continuation of this task. Okay? So that's why it's a continuation. It's kind of like maybe if you do any kind of functional programming, you pass forward a continuation or a callback, right? So if you do this, the idea is that every time the next task runs, it'll use the next cursor, which will pick up at wherever you left in your data store scan, do the next little bit, then it'll do another task, and so on. The problem is that if the task queue ever fails or your app ever fails, you get a fork bomb. Each task enqueues new tasks. They fail right after they enqueue tasks, then they start again, they enqueue more tasks. You actually get this exponential explosion of tasks. If you've ever done basic continuation passing on App Engine and hit an error or had a syntax error or anything, you've probably had this happen to you. And it's really terrible. So the task, basically one fails, and then it leads to 2, and then to 4, and then 8, and on. It's just really terrible. So that's the wrong way to do it. And it doesn't really take much to prevent this from happening. All you have to do is name your task. That's it. So in App Engine, tasks have this property called a name. You get to assign it. Here I'm just assigning it a sequence number. I'm saying the generation number starts at 0. So the first task is generation 0. Then I do 1, 2, 3, and I add 1. Okay? So it's exactly the same code. Like, do the query, figure out what you're going to do the work for fan out, then enqueue another task. Okay? But you'll also notice at the bottom, I'm sending some emails after I enqueue the next task, as opposed to before. And the reason I do that is because it lets me actually get more parallelism. Essentially, I'm querying for the work to do. I figure out where the endpoint is, and then I immediately enqueue the next task to do the same thing before sending my emails. Because sending my emails is a high latency activity, right? So I should be able to pass the baton to the next task to find the next people to send the emails to, and then still do my work. So what you end up with is this nice kind of cascade of tasks, where each one queries for the next little bit of work, then enqueues the next one, and then so on and so forth. So they actually will be overlapping as they execute, which is really nice. And because you've named them, our task queue system on App Engine has the ability to tombstone tasks. That means that you can only add a task with the same name once every 7 days. That's how it works. So if you re-add the same task, it'll raise an exception to you and say, you have already added this task. The other thing is that, besides just your own coding mistakes, the task queue isn't a perfect system. It might run tasks more than once. That's part of the kind of scalability trade-offs that we've made with a system like that. So this kind of gives you a level of idempotence on your tasks. Basically, you're saying, hey, if this task gets added multiple times, that's all right. So in this case, task 1 and task 3 spuriously have run, and they maybe send new emails to that small number of people, but they don't cause a fork bomb. They don't cause an exponential number of additional tasks to be added. Okay? So every time, say task 1 spuriously gets called, it'll enqueue task 2, and that will return an error saying, this task already exists, so don't do the next piece of work. So this is the way to do continuation passing. It's basically figure out the cursor, add the task, and then actually do the work you want to do with names. So this, like I was saying, this isolates the failures in your spurious retries, and it lets you execute the work in parallel, which is great. The other thing is that it works really well with asynchronous APIs. So if you ever have a situation where you have high latency, you want to iterate through a bunch of things in parallel, and each one takes about 10 seconds, but you want to get them all done in a short period of time, if you do the query at the beginning of the continuation, you can start passing that baton immediately. And so as soon as you enqueue the task, it'll start running within 5, 10 milliseconds. So you'll get 50 threads running in parallel, something like that. So that's a really nice way to get a lot of work done all at the same time and do fan out for a higher level of parallelism. And so we use this technique in the hub, and we do between 100 and 300 worker requests per second all day long using this style. So it's really effective. It works very well. And we've had async URL fetch in Python. There's been Java support since February. There's also some really cool tools in Python and Java for doing asynchronous data store calls, which you should definitely check out. Async Tools and Twig. They do a lot of asynchronous stuff with futures, and it's just really great as a programming model. It's much more efficient than maybe what you're used to. So definitely check those out. OK. So next up, we got a lot of ground to cover. That's why I'm going kind of quick. That makes sense so far? Any questions so far? Yes?
Every time when you execute these things in parallel sequence,
Yep.
you lose the atomicity.
So he said, yeah, every time you run these things in parallel or in sequence, you lose. Yeah, I'm repeating the question. So the question is, every time you run tasks in parallel or in sequence, you lose atomicity. Yes, you lose atomicity. Absolutely. That's part of the deal. I'm getting into how to keep that if you need to. That's part of the trade-off of fan out. Basically, you're saying, I know I need to fan out. And then if you need to apply some kind of atomicity or sequencing, then that's where you get into transactional sequences. So yes, natural question. That's why it's the next topic. So how do you guarantee atomicity across tasks? OK, so what is a transactional sequence? So we've had this for a little while. Some people don't know it, but you can actually use data store transactions with tasks at the same time. What that means is that you can commit a transaction and a task at the same time, which means that the task will not ever run until after the data has been committed, and that the data won't get committed unless the task will run. So you are guaranteed that they will both be in or out, right? You don't have any extra tasks, and you don't have any missing data. So that means that you have strong consistency when the task is run, and you can do all kinds of really cool things with that pair. Specifically, what it lets you do is something like roll forward semantics to fan out data. So I'll explain what that is. But in a nutshell, you can have roll forward materialized views. So what is a materialized view? If you're a database person, you probably have heard that term before. So a materialized view is just a query that you save back into the database. That's all it is. Do the query, save it back in the database. The reason you want to do that is because you want to read from it a lot. You want to cache it a lot. Or maybe it's an index that's more complicated, required some work that you don't want to have to keep doing. And a lot of the time, it's eventually consistent. So with a materialized view, you don't care if it's perfectly transactional as long as it's eventually correct, provides a good picture of what's going on. And so a materialized view also lets you do all kinds of cool tricks. Like you can do incremental aggregations, like counts and sums. You can do natural and left joins pretty easily. And you can do all kinds of filtering and querying on those materialized results. So you can do a level of richness in querying that you couldn't do otherwise. So let me show you what I mean. So here's a SQL statement. This is something that people do a lot. Grade would be like first grade, second grade, as kids get older. not like A, B, or C. So we have Bob and Daisy on the student table, what grade they're in. And here I can figure out, select grade, count stars, count from student, group by grade, basically. So I'm saying, how many people are in each grade? It's a really simple statement you can do in SQL, and it's something that's actually kind of hard to do in App Engine. So how would you build this on App Engine if you wanted to make sure that it was correct, like that it eventually always came to the correct answer? And so what you could do is you could build a materialized view, which is this lower table, which gives you the grade to count mapping, right? And then you can do all kinds of cool stuff like that. Like you could render the front page of people with grades, or maybe the dig main page, a bunch of stuff. So let me show you how to do that on App Engine. So this is the same model. Same model as SQL. I'm just kind of giving you a little more syntax around it so you understand exactly how it works. So we have a student model class here. That's the person. That's the first table. It's who and what grade they're in. Okay. Then we have this marker class, which is actually just a random entity. I'll explain how it works. This is what we use for sequencing. And then at the bottom, we have the group count, which says for each grade, what is the count? So that's the actual materialized view is the group count. That's what that is. Okay. So this is the idea. You want to have roll forward semantics. That means the data rolls forward. That means that at any time, all that matters is what is the next thing in the sequence of events. All you care about is the latest value. So anytime data falls behind, you just want to roll it forward. That's all you care about. That's what we're trying to achieve. We're not trying to have perfect transactional consistency across all of our inputs and our aggregations. We're just trying to make sure that it's eventually correct so that it reaches some stable value without any potential conflicts. So we have Bob. Let's say that Bob gets held back or pushed back, maybe got in a fight, I don't know. So we're changing his grade from 4 to 3. It's sad. And he's a student. And so we make a new child entity. That's kind of a weird, weird relationship. But let's say the student has a child entity, which is the marker. Okay? So you remember this marker. The marker has a sequence number and it has a property of whether or not it's present. I'll get into what that means. But when Bob's grade change comes in, this is someone typing in the change, we increment the sequence number. Let's say it was 16 before. This is just any sequence number. It's just an ordering for the events, the changes. So this is change number 17 that we're doing. We apply that to this child entity, and this is part of a whole transaction. So then we transactionally, step 3, enqueue 2 tasks. One task says, hey, update the old value, the old aggregation. Say that Bob is no longer in the 4th grade. And the other one is update the new value and say that Bob is now in the 3rd grade. So we can update the materialized view from the source data. But we update the source data in a transactional way so that it's consistent and atomic on the source. So then we commit the transaction and then the tasks run. So let me just show you the code for the update. So this is the update function. I'm defining a transaction. I have, as parameters to the update function, I have the name of the student. I have the new grade that they're going to be in. And I have their student ID. So if the ID exists, like this isn't a new student, I'll get the student, and then I'll keep track of what their old grade was, and then I'll update their grade to the new grade. That's just a little swap line, that old student grade. If they don't have an ID, then I'll create the new student, assign an ID by putting it, and then do the same thing. And note that they didn't have an old grade, so I don't have to remove them. Then I go and retrieve the marker, which is the sequencing entity. And I pull it out of the data store. If it doesn't exist, I also create it. That's this if not marker, marker equals blah, blah, blah. That's just kind of get or create. And then I increment the marker sequence number. So this is how I guarantee atomicity of this student's record and what grade they're in. Okay? So this is just finding the student and then saying they were sequence number 16, now they're sequence number 17, and their grade is changing from 4 to 3. So that's what I've done. I've assigned their new grade level, kept track of the old one. So you see, old, comma, student.grade equals student.grade, comma, new. So that means old will equal the old grade, and the new grade will equal the new grade. Okay, that's all I'm doing. And I'm saying that this is the 17th change or the nth change to this user's data. So it's atomic. It's in order. So then I put those back in the data store. I enqueue a task transactionally. That's what that transactional equals true is. I say this student ID has this grade now. The sequence number is, say, 17, and they're present. That means that they're now in this grade, okay? Then I also say, hey, if the old one is not none, that means they had a previous grade. That means that they've been moved between grades, that they graduated, whatever. Then I also enqueue another task for the same student, except grade is old. So I take the old grade, and then you'll notice that I use the same sequence number, but then I set presence to false. So I say that they are not present in the old grade, because they've been moved out of the old grade. That was the point, because we moved Bob from grade 4 to grade 3. And then I run that in the transaction. So I run the transaction and commit the transaction. So all we've done here is change their grade from 4 to 3, and then enqueued 2 tasks transactionally that are guaranteed to run with a sequence number. So, OK, this is the models again, just to show you. So that's the sequence ID, the marker. So now what happens? So let's say this is our initial state. On the left, we have the aggregation group count for the third grade. Or sorry, for the fourth grade, OK? This is a parent entity, which is the count. This is the aggregation. This is the fourth grade, how many people are in it. That's all there is to it, right? The one on the right is for the third grade, how many people are in it, OK? Now, child entities of these group counts are these markers I was telling you about. These are the things that are used for sequencing. They indicate if a student has actually been present in the aggregation, OK? So you'll notice here that Bob was in the fourth grade. On the left side, he has an entity that says he was present. It has sequence number 16, OK? And it has a plus, which means that he's present. That means he's in that grade. On the right side, you'll see that Bob also has sequence number 16, but he's got the presence indicator of negative, which means he does not contribute to the aggregation. OK? So then what we do is these tasks come in, the 2 tasks that we enqueued before, these 2 here, the run tasks, the 2 we enqueued. They run. So watch the left side. So we do a transaction here, and we update these 2 values. We say, transactionally, Bob is no longer in this grade. Update the transactional sequence from 16 to 17 to make sure that it's ordered, and then reduce the group count from 3 to 2. So we're just taking him out of the grade transactionally. And we're sequencing it with that sequence number. That's how we make sure that we don't mess up. We do the exact opposite on the other side. We do another transaction. This is in a second task. And it updates the group count to 3, and then marks Bob as present. OK? That's all that's going on. So the code to do this, oh, it's not wrapping right. It's OK. All right. So to apply this is what the task does. It has a sequence number. It has whether or not they're present, the new grade they're going to be, or the grade I'm affecting, and the ID of the student. So then it figures out the keys, it starts a transaction, and it says, give me the aggregation count, or the aggregation row, which is the group count entity, and the marker, which is for this student. Is Bob present as part of this aggregation? Then it creates both the group count and the marker if they don't exist already. And then there's this important line. If marker.sequence is greater than sequence, roll back. This is the kind of magical part of this, OK? This is when I'm talking about roll forward semantics. This is what I'm talking about. So if we accidentally moved Bob from grade 4 to grade 3 and then back to grade 4 again, we don't care what order the events come in, because we know that when we changed it, it went sequence number 16, 17, 18. So if you look at the aggregation, and 18 is already there, marker.sequence equals 18, and the incoming task is for sequence number 17, you're like, oh, I already knew this. I already applied this. I don't care about this anymore, because it's an old update. I can ignore it. I'm rolling forward my data. That's the point. So you can just drop the old stuff. And the rollback will actually cause run and transaction to return without any kind of exception. So it'll look like it was successful, which is what you want. So then on the next step is in that transaction, I just say, OK, this is transaction number 17. I assign it. And I keep track of kind of what whether or not they were present before. That's what that old value is. I put the sequence number back in there, db put marker. That's what I do. That's me updating the sequence number to keep this atomic property. If they were present before, then I subtract. If they are present now, then I add 1. I could probably write that better, but I'm just trying to make it really clear. If the count is now 0, that means there's nobody in the grade anymore. So I just delete the grade. I don't want that table, or I don't want that row in my aggregation table. And then I either put the group or I delete it. And then I run that in a transaction. Okay? So again, the idea is that we're rolling forward these 2 independent entity groups at separate times, but able to keep atomicity across them. That's like the really cool thing. Just to hit you over the head with this again, so here's the sequence of what we're doing. Number 1, change the student grade. 2, increment their sequence number. So 16 to 17, old grade was 4, new grade is 3. 3, enqueue 2 tasks. 4, tasks are running. We fetch the grade group. We compare the sequence numbers. We see that the current one is 16. 16 is less than 17. We allow the transaction roll forward to happen. We increment the count. That's all there is to it. It's really simple. So let me show you this. I have this running. Let's see. I think it's this one. OK. So this is my little demo. I'll be making this code available soon. So there's me in 6th grade and Jim in the 2nd grade. I can add Alon in the 4th grade. Click Add. OK, there we go. Now I'm going to move Jim into the 4th grade. See if it reloads. There we go. OK, so you see 2 students in grade 4. So you're seeing, now this happens so fast, you're like, well, Brett, you're just doing that under the covers, whatever. It's happening so fast. Well, that's because task queues run really fast, you know. But just to show you, these are my admin logs. So you'll see, here's a 302. That's what I return when I, 302 right here. That's what I return when I have a successful post. And you'll see 2 work items run. 1 removing it from grade 4, and 1 adding it to grade 6 for the same student. Okay? That's all I'm doing. Really easy. But that happens so fast, you'll see, look at the times. 33.36, 33.72, 33.73, 33.8. So the tasks ran before my browser even reloaded the page. It's pretty cool. OK, so some final details about this. So each aggregation row is its own entity group. That's how this works. That's how you guarantee that the aggregation rows stay consistent within themselves. You update them in separate transactions, and the order of the task application doesn't matter. And then that marker entity, child of each row, basically indicates the presence of that student in the aggregation. So that's how you do this. That's how you bridge the transactions across these entity groups. And the roll forward part is that you can just ignore old updates because you don't care. It works really well for cumulative operations, count, sum. If you're toggling presence, it's really easy. You can actually do some ancestor queries in that transaction because it's across the same entity group. So if you need to do something like sum of squares, it's actually possible. And you can actually use continuations with cursors to do multiple transactions, comparing sequence numbers all along the way, to actually do really elaborate functions on all of your aggregation data. That's more complicated and more expensive computationally, but it's kind of a simple model of doing work like this in a deferred manner. So it's definitely something to check out. And you can kind of keep your aggregations accurate, which is really nice. And then you can fan out. So when the source data changes, you can enqueue multiple tasks and update many aggregations at the same time. So you're not limited to just one materialized view. You can have many different ones for the same data. Now, the thing is, though, the gotcha, is that the maximum throughput is proportional to how many aggregation rows you have. You need to do transactions on each of the aggregation rows as you apply the transforms. So if you only end up having one aggregation row, then you actually are going to be limited to updating how fast that one aggregation row can update, right? And usually you want to limit that to about 1 transaction per second per aggregation row to make sure that you have no conflicts and no rolled back transactions, transaction collisions. So that's a problem. For a lot of apps, though, that are trying to do complicated aggregations, they really don't care. That's actually, they just want the functionality. The other thing is you pay the storage cost for the presence entities. So to even indicate that an aggregation contains one of the students, for instance, you need to write a little row. But that row is usually on the same size. It's about the same size as the actual key of the original data. So it's like 100 bytes or so. You don't have to index it in any way. So you can do some really nice things with those presence indicators to make them really cheap. OK. Why don't you hold off on that one? Maybe I'll just answer that one too. So, all right, so this gets to the next problem. If I'm limited to 1 transaction per second, that's not really good. And I actually need to do a lot of work in batch a lot of the time. And what I find in building a pipelining system is that I often need to do a lot of work in batch. So that's when I want to fan in. So what is fanning in? So it means applying multiple data transforms in a batch, doing work in batches, taking counter updates, aggregation updates, roll-ups of event data, reservations of different resources, doing them all at the same time. For instance, with Reddit or Dig style voting, once a second you could just poll for every update and then save the new values. You only have to apply what's changed since the last time you looked, right? So that's Fannin. You take a bunch of events that have come from a lot of different sources, combine them and aggregate them together into a single batch of work. And this lets you not necessarily, well, you can beat the 1 second per entity group write throughput problem with these aggregation rows because you can batch up your work into smaller pieces. It's also really good for high latency API calls. So if you're doing a lot of URL fetches or doing any kind of complicated data store queries or a lot of these queries at the same time, if you're building an RSS aggregator or you need a lot of throughput, it's really good for that. Make sure that your queues don't back up. So that's when you want to do Fannin. Basically, anytime you want to amortize the cost of doing a lot of work, and you can do that by doing it in parallel, you want to Fannin so that you can do your work in parallel at the same time. That's like a pretty obvious idea. So the problem is that when people do this in the real world, they usually think of it this way. So in the real world, like the outside of outside of Google, I guess, fantasy land of my wilderness. So they have a queue, and they have a queue moderator, and they have a bunch of workers, and they pop off the head. Maybe they grab 5 at a time, or 20 at a time, right? And that's how basically every other queuing system out there works. And it works really well for a lot of things. The problem is the workers are always running. And then what happens is, remember, we're trying to build a pipeline here. So how many polling workers do you need to make sure that if you're inserting 50 tasks a second, that each one is serviced within 500 milliseconds? And then what if the tasks take a long time, each one? And then how do you make sure that the workers don't step on each other's toes, right? Like, there's a whole series of problems that come out of polling-based workers. They can batch, but they can't actually guarantee the latency that you need. So I would claim that polling workers actually don't work for offline processing. Sorry, polling workers are offline processing. They don't work for pipelines. That's what I'm saying. Polling workers cannot do pipelines. They're not dynamic. The latency is not low enough. You have to have workers allocated for your peak load at all times because you need to make sure that you can guarantee those that latency margin. And it basically eliminates, if you're doing polling, it eliminates the benefits of the push-based task queue that App Engine has. Okay? So what I would like to use instead is a fork join queue. Okay? What a fork join queue is, it's a queue where, as work comes in, we fork the items apart into different segments. Okay? And then we make sure that all of that work will start within a fixed interval after arrival. So each piece of work will be guaranteed to run within 500 milliseconds. Then we execute the work in those batches. So we fork it and then execute it in batches. And then at any time, we can join that work back with some other data records to leave the system. That's the join part. That's optional. But it's part of the same kind of idea. So I'm going to show you exactly what I mean. So here's a fork join queue that uses the data store along with the task queue. So ideally, I would like to have 2 batches run in parallel for 2 500 millisecond periods, let's say. So time is going to the right. So a new work item comes in. I insert it into the data store. So this is some work I need to do. This is a feed I need to fetch. This is a vote on an item that I need to upvote. And then when I insert that item, I also insert a task with an ETA 500 milliseconds in the future. So presumably, that task will run after the first batch has queued up, right? That's what I'm trying to do. So then I insert another work item. And then I insert the task again, but the task is already there. That's that first property when we were going through continuations. That's what happens. The task is named. So you're guaranteed that if you insert it 2 times, basically, that it only will run once, okay? So that's the Fannin. That's the magical part, that the task is already there. So the task will only actually run once. So then I can insert more work. Again, I get the task conflict, and it just skips it. Same thing, so the batch is full. I've got a whole 500 milliseconds worth of work. And then I execute the task, and I take care of that batch. Really straightforward idea. Now the next batch starts. Starting queuing work again with a task that starts after the batch 2, and so on. So it seems great, right? It's really easy. The problem is that how do you coordinate when the batches start and stop? So people are like, well, let's just use the clock, right? Every 500 milliseconds, just pick the current time and then pick on the clock where you want it to start, and boom, you got it. Except clocks aren't in sync. It doesn't work like that. Even with NTP, it doesn't work like that. I saw a server the other day, it was 40 minutes off. So yeah, not good. So we need another way to do that. And then there's another problem. What happens if there's a race condition right at the edge where the task just starts to execute right as another, or the task executes and finds the work it needs to run just as another work item is inserted? How does the task know to wait? So we actually kind of need a lock there. We need to make sure that the task doesn't run until the entire batch is committed. So that's a problem, right? Similarly, if we have one of those machines that has a terrible clock, what if it inserts into the wrong batch? Or inserts into a batch that already executed a long time ago? We needed ways to prevent those things too. So time alone doesn't work. We need something better. So let me show you how to do it. So here I have some, this is me counting again. Next year I'm going to wear a cape. That'll be good. So I have my sum here, which is an aggregation of me counting. I have my work, which is deltas, basically, that I want to apply to the sum. And then each piece of work has a work index, which I'll explain what that is. And then the sum has a name. Okay? Really simple. But you can think of the sum as saying, like, this is the most popular dig item right now, and my work is my upvote. Okay? So, oh man, my wrapping does not look good. I'm sorry about that. It'll be okay. Yeah, this fits. All right. So insert. This is inserting a work item. This is inserting a upvote or a delta, a positive delta, negative delta. I have the sum name and then the delta amount as my 2 parameters to the function. I will call memcache get on an index. Okay? So this is a counter that represents my batches, my batch count. So what I want to do here is instead of using time for batch 1, batch 2, so I have 500 milliseconds in the future, 1 second in the future, 1.5 seconds in the future, what I'm going to do is actually assign sequence numbers. Batch 1, batch 2, batch 3, batch 4. And that's how I'm going to assign these groupings of these tasks. So I do that with memcache. I do a memcache get on the index. If the index isn't there, I add it starting at 1. And so then I have my work index. So I know this is the next batch number that I'm going to use. Then I look in memcache, and I look at the lock. This is a reader-writer lock that I'm doing in memcache. Okay? Memcache is extremely fast for doing a reader-writer lock. So I do a memcache increment, and I increment the lock with this name. I'm formatting a string here. I'm just putting the sum name and the index number into a memcache key. Okay, that's all I'm doing. So if my sum were stuff, it'd be stuff-lock-index, so in 400 or something. So I do a memcache increment of that. That's atomic. And the initial value I set to 2 to the 16th. I'll explain that in a second, why we need to do that. Now, this will get a little hairy, and I'll come back to exactly how it works. But if the number, so I do the increment, it gives me back the new value of this lock, this reader-writer lock. It's more like a semaphore. If the writers is way less than 2 to the 16th, or anything less than 2 to the 16th, I basically know that this lock is no longer, this index is no longer available to new writers, okay? So you cannot use this index anymore, is what that negative is, that if writers is less than 2 to the 16th. That's saying the index you just selected on the first line, memcache get, this index you can't use anymore. That solves the race condition of the task queue and the batch coming in at the same time. So in that case, I decrement the lock. I'm like, all right, drop this lock, and I return false. This failed. I didn't get to insert the work item. If you want to make sure that's totally reliable, you just keep spinning until you get one. Memcache is fast enough that you usually have to try, like, at most twice. Okay? But that's just solving the race condition of the synchronization at the end of the batch. So then once I have incremented the lock, that means I have incremented the writer lock. I've registered that I am a writer for this lock. I'm going to be writing so that, keep track of that as like a semaphore. So I add one to that reader-writer lock. Then I take my work. I set the delta to whatever I supplied, add 1, minus 10, whatever. I set the work index property to the index I got with the sum name, and then a hashed value. I'll get into why. Newth hash is just Donald Knuth's hash. And then I put in the work, commit it to the data store. Then I do the batching part. And all I'm doing is I'm taking the present time, and I'm saying, I want to have some work start 1 second from now. So I take the current time, add 1 second, ETA. This is me setting an ETA. You could do it with a countdown, too, either way. But the important thing here is I'm setting the task name. The task name is set to sum name plus now over 30, I'll explain why that's there, and the index, which means that if 100 work items all do this at the same time, they'll all fan in magically. One of them will succeed, and all the rest will go into this exception handler. Task already exists there. And I pass there, which means I don't care. Okay? Now, once I've put the work item, so that last line, so I've created my work item. I've assigned it a batch number. I put it in the data store. I've enqueued a task. Then I decrement the reader-writer lock. That means I'm no longer a writer on this lock. I'm done. And I return true to the writer. Okay? So that's relinquishing the writer lock. So this lock allows multiple writers and a single reader. That's what we're trying to do. All right, let's take a little break. A lot of code. So now joining. This is taking all the batch items and running them together. So first thing I do, this is the task running. This is the task I enqueued. That's where the join's happening. So all of these input items enqueued the same task, 500 milliseconds in the future. Eventually the task wakes up and it starts running. And it knows its own index because it's encoded in the name. So, see that task queue add name equals? The index is the last parameter. It knows its own index, okay? So when the task wakes up, it knows its name and its index. So then it will memcache increment. It'll push the batch index forward. It says, OK, batch number 400 is done. I'm closing the gate. Push it forward so that batch 401 has to happen. Okay? So it's pushing things forward. Then it goes to the lock, that same reader-writer lock, and it decrements it by a huge number. And this is the you missed the boat signal. This basically handles the race condition exactly at the borderline when the items are sequenced in such a way that the writer beat the task of getting the index before this first increment. So basically, the writer grabs 400 and then starts committing. Or sorry, it grabs 400 and then starts to increment the lock. So that's the race that you're trying to solve there. And by decrementing it massively negative like this, decrement 2 to the 15th, that's what lets us do this if writers is less than 2 to the 16th. All right? So it's just making sure that I thought I acquired the writer lock, but I actually didn't. That's all you're able to detect. So if writers is less than 2 to the 16th, what that actually says is the task is already running right this very second. Is actually 2 threads running at the same time. It's giving me a synchronization primitive between my active writing code and my reading code. That's what that does. That's the actual mechanism. So now, in the task, because I have multiple threads running at the same time, and I have the synchronization primitive, what I do is I need to wait for the writers to finish. So sometimes the data store might take up to 1 second or 2 seconds, depending on what you're doing, how big your data is, whatever. So here I actually just busy wait. And I keep getting that lock, its current value, and I wait for all of the writers to finish. So as soon as the counter goes back to a known value, basically the 0 point, then I'm like, all right, cool, all the writers are done. I can now do my actual work, okay? And you can set a timeout here to give up after a few seconds. But at the end of the day, all we've achieved here is we've been able to batch a bunch of work up at the same time so that it'll execute in parallel. So this is how I actually get the work. It's just indexed by the work index. I say, give me all the work with this index, give it all to me. So do a filter, give me a list of everything, sum up all the deltas for all the results, and then apply them in a transaction to my sum. Okay? So results equals, that's the query to get all the work with a certain index. Delta is just the sum. The transaction just gets the sum, creates it if it's not there, applies the delta, and submits it. At the end, I delete the items if I wanted to. So you see again, inserting work into the data store. And as the work gets inserted, it gets a batch sequence number, inserts a task with that sequence number. Then the next work items do the same thing, right? Same sequence number that they have. As soon as the task runs, it prevents that sequence number from being used again. And then there's some extra fancy bits around a reader-writer lock to make sure that this case, where you insert the work right at the exact same time the task is running, doesn't cause you to drop things, okay? It guarantees it completes. That's the hard magical part about this. OK, so a demo. Let's see. All right, so this is really a great app. This is like one of the best ones I've ever written. It just says true. So that just means it inserted some data. I was going to run HTTP perf, but apparently my laptop doesn't have make right now. That's news to me. Yeah, I know. Sad. So, and so again, I'll show you my admin logs. Hopefully I caught it fast enough. OK, so you see here, these are me doing increments with name. The sum name is food. The delta is 1. They all get the same sequence number, insert a task, and then the work will actually batch it up. So it says I'm combining 5 tasks into a delta of 5. That's what it did. And there are no race conditions. It's fanned in. It's much more efficient. You can do all the database work in parallel. It's really great. So details, again. The task names are the Fannin mechanism. That's the magic here. That's how we do it. We use the task ETA for the periodic batching. We use memcache for reader-writer lock so that the batches can coordinate to make sure that you don't start reading before the writers are done. And then we use spin locks to make that coordination work correctly. And last, we use the data store to go and find the actual work. So we applied this work index to our data, the batch ID, the batch number. So we actually just query for it in the data store. And then if you do get any drops for whatever reason, like if you have a more lossy data model, you could use an offline job to pick those up. But given the scheme, you shouldn't have to. And it scales. What a concept. So depends on your batch size, obviously the data format you have, the model you have. I just ran a few tests with this code. The model I was testing with was larger, but I can insert basically up to 75 items per second. The latency didn't change. So just batching it up every second worked really well. It's great. Now, some important details about the performance. The work index has to be a hash. You have to hash it. That's why I did the Nuth hash. And the reason is that you need to do that so that you distribute the load across Bigtable. A naive batching implementation might use a timestamp to do this. The problem with timestamps is that they're always increasing. So in Bigtable, you're always writing to the beginning of the same row. Bigtable always does things in order, right? So if you are ordering things by time descending, you're basically always writing into the same row. So every time the tablet gets overloaded or gets too much data, it's going to split itself in half and then keep doing it. But you'll just keep pounding the same one over and over again. You don't actually split the load. So by putting a hash on your work index, you're making sure that you fan out your work so that some of your writes go over here, and some go over here, and some go over there. That's how you get the parallelism of the Fannin. The other thing you need to do, if you really want a lot of throughput on this, is to eliminate all the other indexes you have, like global indexes. Composite indexes are fine because usually they're prefaced with a unique key. But global indexes have the same problem, where if you're writing the ETA or update time of an entity that's in a global index, that top of the list big table tablet server will be unhappy. But the other thing is, yeah, I say here, you can keep indexes of your box carrying transactions. So what I'm saying there is that if the whole point of this is just to make it so you can do more work per transaction, then you really don't care so much about the big table fan out. All you're trying to do is, say, apply 100 manipulations to the same entity group at the same time. So you're just trying to do all your writes and combinations so you can kind of move faster. But you're not actually trying to do like 100 updates per second. Right? The last thing I don't have too much time for, but it's just this magic batch period equals 0. So in my testing, which is fun, and I've been using this, I meant to mention, I've been using this in the PubSub hub for a few days now at scale. So it works very well. It actually reduced my total footprint by about 40%. So it's pretty serious. I actually use a batch period of 0. And what that means is I wait for as long as the data store takes to put. That's my batching period. So I start that put, and that's how long I'll wait. So sometimes it's 50 milliseconds, sometimes it's 10, sometimes it's 100. So it just kind of expands based on my latency. And that kind of creates a self-regulating system that's really cool. So you can experiment with that, and there's some more advanced code to do that. Something to just think about. All right, I've only got a few minutes left. I just have one last slide, and then I'm basically done. All right, that was probably a lot. That's the most code I put on screen, so I appreciate you bearing with me. So hopefully, if you've been thinking about this, the obvious combination of this thing is you can take Fannin fork join queues and the transactional sequences and materialized views, put them together and get something really cool. And that's right, you can. That's the point. That's what I'm getting at. This is a huge wall of text. Don't even look at it. Don't even look at it. It's just for me. OK. So here's what you do. You have a fork join queue that batches once per second. The user updates some data, like their votes. OK? I upvote this item. They insert that data, and they get a work index for their fork join queue and apply that to their vote. Okay? That's basically saying they add it into a fork join queue. Then they transactionally insert some tasks to go and update their materialized view. Then you also go and insert optimistically, you insert some named Fannin tasks. That's to do the magical batching that the fork join queue requires. And then later on, the Fannin worker will query for all of the votes that have come in the last 1 second. And then it'll do a transaction on all of the rows that make up that aggregation, like the total votes for an item. It'll fetch all of the markers. It'll compare the batch work that it just got in with what's present at the current time. It'll figure out the difference of what's present and what's not present, like if someone changed their vote from upvote to downvote. It'll do that with sequence numbers to make sure that it has roll forward semantics. And then it'll update the aggregation row and commit. So what does this mean? What this means is that you can actually get a lot of throughput out of those aggregation rows I was telling you about. The materialized view thing I was telling you about, you can actually write to those like 100 updates per second, but you just have to do it in batches of 100 once per second. So you can combine the materialized view stuff I've told you about today with the fork join stuff, put them together, and get a very high throughput aggregation system to do all the aggregations you want, which is just great. So please build this and send it to me or our team. We'd love to see that. It's something you can do in user space. I wish I had more time. So yeah, thanks for bearing with me. So OK, last slide. Future direction. So now you're probably asking me, this would be a lot more efficient if I could go faster, longer, batch more, right? And we're working on it. This is on a roadmap. We want to have background servers. These are servers that have no wall clock limits. That means we don't have a 30-second deadline anymore. Something that's important to us for the purpose of pipelines like this and for the next talk about the Mapper API. We want you to be able to chunk through these Fannin queues in bulk, like huge amounts of bulk. It would also be even faster if I could have addressable servers running on App Engine, so that every time a new worker item comes in, I would just send a remote procedure call to some running server and have it queue it in memory. That would make this extremely fast. It would be lossy, but it would be an order of magnitude faster. So we're working towards these kind of efficiency goals for both pipelines and for offline processing, both in the form of background servers and addressable servers. So it's on our roadmap, something that we think is really important. OK, we've got a little bit of time for questions. TinyURL App Engine Pipelines is where the questions are. This is my blog, if you want to follow me. And thanks for sitting through that. Let's see, I think I have to, yeah, thanks. Let's see what happens here. I think there's a mic here and a mic there. Don't have much time. I'm going to be going, well, directly after me, before you leave, there's a talk from Mike Izatsky, who's also on the App Engine team, talking about the new Mapper API. I really encourage you to stay for that. He's talking about Mapper and the report generation and batch processing on App Engine. It's a really good talk. Really encourage you to check it out. And it has a lot of kind of, it's not overlapping with my talk at all, so it's very useful. So let me see if there's any upvoted. Will there be an extension or removal of the 10-second limit of the requests to external websites? So it's a 30-second limit now. And like I said, we're working on background servers and addressable servers to oh, I gotcha, for URL fetch. Yeah, I think Kevin said yesterday during the Fireside chat that we're trying our best to raise it into the 30-second range, and we understand that people want to go up to multiple hours or indefinite. That's something that we're aware of, and we're working towards. The memcache increment can be a bottleneck. What will be the max throughput? I've maxed out memcache at like 120,000 requests per second. I have a feeling that's not going to be the problem. So, I mean, that's cool if you're doing that. That's great. That's like massive success. Cool. Let's take one from public. Yeah.
Your ETA, was it based upon an estimated amount of work for the task, or was it a constant because you know how App Engine performs?
It depends. So yeah, so the question is the ETA on the batching based on some constant idea, or is it based on how the work I'm doing, or is it based on some characteristic of App Engine itself, a characteristic of App Engine itself? So both. In the case of transactions, I know to be really safe, I shouldn't go more than 1 transaction per second if I'm actually trying to write a lot of data at a time. That's like just a good rule of thumb. For other stuff, if I'm doing URL fetches and I know the average latency is 5 seconds, doesn't really help to batch more often than that, maybe. So it really depends on the problem that you're dealing with. If you know you have a lot of latency, then it helps to batch a lot. For instance, if you're doing 20 URL fetch calls, you can do them all at the same time. And then you can use one thread to hold on for 20 seconds of latency or 10 seconds of latency. So you can eliminate your waiting costs by batching asynchronous calls together. So yeah. Yep.
So looks to me that you're trying to build a singleton pattern on top of data store using materialized view, and the other one on a transient memory on memcache. In the case of data store, if you run parallel tasks.
Okay. Yeah.
You run into, in an optimistic concurrency control, you run into stale data. In the case of transient data, you lose the data if the transient memory goes, out of. So
what was your question?
So is it easier to have something like a transactional memory, like a singleton pattern, instead of doing this?
So yeah, so that's all right. So basically, the question is, why go to the trouble like this when you could just have global transactionality?
Like a singleton, which is across distributed system, of course.
Right. So if you want the richness of the queries that we have, you can't achieve that. You cannot achieve global ordering like we have with our data store and also be a singleton. It just doesn't work. Like we have built something that, it's like the CAP theorem, right? You can't get everything. And so we've got a nice trade-off of these properties that lets you scale extremely wide, let you do rich queries with consistency. But we have trade-offs that come out of that. And one of them is we can't apply global orderings like having a single database. But a lot of people really want that, which is part of why we've announced that we're going to have a SQL server so that people can get that singleton locking performance that they want, functionality that they want.
The addressable servers, is that going to solve our problem of trying to have a transaction?
It could. Why don't you come to the office hours? I think that's a really advanced question. So we should talk about it then. Yeah. Yes?
What's the limit on number of simultaneous task queues running, and is that something we can control?
So you're saying tasks per second or threads?
Tasks that are running simultaneously.
Yeah, it depends on their individual throughput. I don't remember what the number is offhand. If you come to office hours, we should have one for you. But I think that the total is 50 tasks per second right now. Is that right? Or is it higher? Yeah. So. Sorry, what? Oh, what about BigQuery? How does that relate to this? That's a good question. I don't know. I have to think about that. Yeah, big lines. Yeah, exactly. So BigQuery, I guess, is offline processing, data mining. Yeah. No, it's not. BigQuery is. I'm pretty sure you upload a huge amount of data and then delve into it. Yeah. So, we have time for one last question.
So, just curious on the real-life example on this. What's happening during the scheduled outage when Memcache is not available?
Right. Exactly. Well, when Memcache is not available, the data store is also not available for writes. So in my case, with the hub, I can't do anything anyway. So I just return 503s because Memcache is down, and then I just, like on the hub, that's what I do. So,
so you don't schedule a whole bunch of tasks that are just accumulating during that time?
So the task queue will do its own backoff, so that if it knows that if the data store is no longer can do writes, you can determine that. The only thing that stops during the kind of scheduled maintenance is writing new tasks and completing tasks. But all the tasks that were already there will complete after the scheduled maintenance because they already have work indexes assigned, and the data items do, and the tasks are there. So if Memcache disappears, they'll check for the lock's not present, and then they'll just go along their way.
Okay,
so if Memcache disappears, the tasks will still complete.
But during the outage, there's no new tasks that can be generated?
That's correct, yes. That's part of the trade-off, yeah.
Thanks.
All right, that's it. I'll be outside to answer your questions, but please come to the next talk with Mike Ozatsky. It's a good one.